This is the AP Calculus BC section 6.3 intro video, and we're going to be looking at separable differential equations and then a little later on logistic growth. So we have looked at separable diff EQs for quite a while. We're going to kind of formalize this a little bit and look at some more challenging examples. So let's take a look here. Whoops, there we go. Let's take a look here at what we're going to do. So the concept of separable variables is very important here. Of course, not all differential equations are separable, but the ones we will look at are. So before using integration to solve a differential equation, we're going to have to use some algebra, some kind of manipulation to get all of the y terms on one side and all the x terms on the other side. The solution to a differential equation will end up being the function that, if differentiated, would give you that differential equation. So we're just trying to undo the derivative that has already been done. The solution has to be a function, has to be differentiable over the largest interval containing the initial condition, and of course, if we do everything right, it'll still satisfy the original differential equation. So we're going to start off by doing a couple of general solutions. We've done these before, and so these would be hopefully some good warm-ups, and we'll get into some more challenging ones here soon. So let's take a look at number one. Okay, so with number one, if we are going to separate the variables, this is going to be one of those cases where cross-multiplying will do that for us. So if I cross-multiply, I get y dy equals 3x squared dx. Once the variables are separated, of course this is a really important step. From a grading perspective, if that step is not shown, it's very likely you will be getting no points, as in 0. So please do make sure that you actually write that step down. Okay, once you've done the separation of variables, we are going to integrate both sides. Integrating gives us 1/2 y squared is equal to 3x cubed over 3 plus c. Of course, the 3's cancel out. I would then multiply everything through by 2, so y squared is equal to 2x cubed plus 2c, and of course we've talked about this in the past. 2c is just some other constant, and so I'm going to represent that with just another c, realizing that those two c's are different. We've used the subscripts before, but I think I'll forego that for now. And then finally we would square root both sides, so plus or minus the square root of 2x cubed plus c. So that is an example of how we could find a general solution. Of course, what characterizes the general solution is plus c. So maybe, if you want, you can pause the video, try number 2. I'm going to go ahead and proceed with number 2, see how it turns out. So here is, let me scroll a little bit here. Here is number 2. So once again, we are going to separate the variables. Looks like it might be a little bit more challenging. Let's do a couple of steps. 1 plus x squared times y prime equals 2xy. I think I would add the 2xy to both sides. The next thing I would do, probably, I'll do this right here. I'm going to rewrite y prime as dy dx. Still, it's not super obvious what needs to be done, so I'm going to go ahead and divide the 1 plus x squared over to the other side. That'll give us dy dx is equal to 2xy over 1 plus x squared. And now I'm going to start collecting my x terms on the right and my y's on the left. So I think what I'll do is I'll multiply both sides by dx and divide both sides by y. That would give us dy over y is equal to 2x over 1 plus x squared dx. So key step right there again, we've shown that the variables are separated, and once we've done that, we can now find the antiderivatives. So we can integrate both sides. The left side ends up being ln of absolute value of y. The right side, it's obviously a fractional integrand. The right side ends up being natural log. I know it kind of looks like arctan, but it's natural log because the derivative of the bottom is the top. So natural log, absolute value, 1 plus x squared plus c. So in solving, we need to get the y by itself. So we're going to e both sides. That'll give us absolute value of y equals e to the ln of 1 plus x squared. And there's no way 1 plus x squared can be negative, so I'll just put parentheses 1 plus x squared plus c. It's important to note that the c is in the exponent at this point. And really at this point we're done. We need an initial condition to determine both the c as well as what to do with the absolute values. So I think I would leave this one here right now. If you wanted to, you could do a little bit of work with the exponent on the right. You could say absolute value of y equals e to the ln of 1 plus x squared times e to the c. Remember, if you were adding your exponents, you're really multiplying your bases. Well, e to the c is just some other c, so we could do this. Then, of course, the truth is that e to the ln of 1 plus x squared is just 1 plus x squared, so you could write it as c times 1 plus x squared. No need to do that at this point, but something that you could do. Okay, so there are two examples there, both of them general solutions, and again, the general solution is characterized by having the c in there. We're going to take a look at one more example where we are actually going to find the c, and those are called particular solutions. So in number 3, the instructions are a little bit different. The instructions do not say find the general solution. The instructions say find the particular solution, and we are given an initial condition, which is right here, and that will help us be able to find our c. So regardless, we're going to need to separate the variables. So separating the variables, I'm going to cross multiply, get y dy equals 6x dx. Once I've separated the variables, I'm going to find my antiderivatives. That gives us 1/2 y squared is equal to 3x squared plus c. Now you can do this in a number of ways, but this is the point in time when I apply the initial condition. So y of 2 equals -2. That means when x is 2, y is -2. So I'm going to plug those in. Make sure you show this step. -2 goes in for y, and a 2 goes in for x. All right, so this left side ends up being 2. The right side ends up being 12. So I'm getting -10 for my c. I'm going to take that -10 and I'm going to plug it in right there where I first applied my initial condition. So it gives me 1/2 y squared equals 3x squared minus 10. My final step here is to solve for y. So I'm going to go ahead and multiply everything through by 2. That'll give me y squared is equal to 6x squared minus 20. And I'm going to square root both sides. So y equals plus or minus the square root of 6x squared minus 20. Of course, plus or minus really indicates that you have a positive y value and then a corresponding negative y value, meaning that if you include the plus as well as the minus, you actually have a non-function. Keep in mind that our solutions have to be functions. And so we've got to pick the plus or minus. We've got to pick plus or pick minus. And the way that we do that is we look back to our initial condition. We're going to look at the y value of the initial condition, which is -2. And so because of that, we are going to choose the negative side of the plus minus. So negative square root 6x squared minus 20, and that would be your solution curve. I don't think we'll look at the domain on this one, but we'll look at the domain on maybe a few others. Okay, so we'll practice these when I see you next time in class. I hope this went well for you. I'll see you then.